I'm going to be talking about Newton's second law for rotations. I'm also going to talk about rotational kinetic energy. Let me make a picture and then we'll continue. So the blue dot denotes an object of mass m moving due to a force F applied to the object, okay, a force of F newtons. So we know from Newton's second law that the linear acceleration of the object is F over m. We'll denote the linear acceleration by a. Or equivalently, F is equal to ma, right? Now, for an instant that the force is applied, we can interpret the object as moving in a circle of radius r. Now, a few seconds later, the object might be moving in a straight line or even in a different circle, okay? But for an instant that the force is applied, we can interpret it as moving along the given circle, such that the circle is such that the force vector is tangent to that circle. Okay, so for that instant, we can define the angular acceleration to be a over r, or equivalently, we could say that a is equal to alpha r, and we could calculate the torque, which is equal to Fr, but F is equal to ma, so the torque apparently is equal to mar, but A is equal to alpha r, so the torque apparently is m times alpha r. Now moving some terms around, we get that the torque is equal to mr squared alpha. Okay? For a simply shaped object with a mass m moving in a circle of radius r, we can define the moment of inertia to be mr squared. Putting all of this together, we get that the torque is I alpha. All right? Now, if you had a rigid body, a complex shaped rigid body undergoing rotation, the torque would still be equal to I alpha. The only difference would be that the moment of inertia would equal a different expression. Okay? Furthermore, if you had multiple forces applied to the rigid body, we could calculate the total torque from multiple torque contributions, and the total torque would equal I times alpha. Okay, so this is a very general result. Now let me restate our result in its general form. This is known as Newton's second law for rotations. Let me also type it out so everything's clear. Newton's second law for rotations. The net torque on a rigid body is equal to the product of the moment of inertia and the angular acceleration. All right? Now, you may know that the law of conservation of angular momentum says that if there's no net torque, in other words, if the net torque is 0 Newton meters, that the angular momentum is constant. Okay? I mentioned that in another video, but I didn't say why that was true. Using Newton's second law for rotations, we can prove that the law of conservation of angular momentum is true. Let me show you how. So For a rigid body, we can denote the angular momentum by the variable L, and that's equal to I times omega, where I denotes the moment of inertia and omega denotes the angular velocity. All right, what would the rate of change of L be? What would the rate of change of L be equal to? Can you see that it would be equal to I times the rate of change of omega? Okay, but the rate of change of omega, that's equal to alpha, where alpha is the angular acceleration, right? But I times alpha, Newton's second law for rotations says that that's the net torque. Okay, so we've just shown that for a rigid body, if the net torque is 0, then the rate of change of angular momentum is 0. Therefore, the angular momentum is constant. All right, the total angular momentum. So this proves the law of angular momentum, the law of conservation of angular momentum. Okay? Using Newton's second law for rotations. Now, let me derive the formula for rotational kinetic energy. And as before, I'll make a picture, and then we'll continue. Suppose you had an object with a mass m moving in a circle of radius r with a velocity vector of length v. All right? So for that object, the kinetic energy would equal 1/2 mv squared. All right? Also, the angular velocity, we can denote it by omega, that would equal v over r. Or equivalently, v would equal omega r. And the moment of inertia, if it was a simply shaped object, would just be mr squared. Okay? Now, let me substitute omega r for v in the kinetic energy equation formula. Kinetic energy is equal to 1/2 m times omega r squared. So kinetic energy is equal to 1/2 m omega squared r squared, or 1/2 m r squared omega squared. Okay? But I is equal to mr squared. So apparently the kinetic energy is equal to 1/2 I omega squared. If you had a complex shaped rigid body, the formula would still be the same. The moment of inertia, however, would be equal to a different expression. Okay, so this is a very nice formula that applies not just to simply shaped objects, but also to rigid bodies. Now, let me do an example. What force applied to the edge of a merry-go-round with a radius of 2 meters and a mass of 50 kilograms will make the merry-go-round move at a rate of 0.5 hertz in 1 minute. Also, what is the kinetic energy after 1 minute? All right, so let's start by listing everything that we are given. So we know that the radius, will denote it by r, that's equal to 2 meters. We know that the mass, will denote it by m, is 50 kilograms. We know that initially, we'll assume that initially it wasn't moving. So omega naught, I'll I'll use that to denote the initial angular velocity, 0 radians per second. The final angular velocity I'm going to denote by omega sub f, and I'm going to convert the 0.5 hertz to radians per second, so 0.5 times 2 pi radians per second. And we know that the amount of time that's passed, I'll denote it by delta t, that's equal to 60 seconds in units of seconds. Okay? So we'll need to look up the moment of inertia for a solid cylinder. We'll assume that that's a good approximation to the merry-go-round. That gives I, assuming we denote the moment of inertia by I, we get I is equal to 1/2 mr squared. Okay, so now let's work with that. So the torque due to the applied force is equal to Fr, and it's also equal to I alpha. So alpha is equal to, where alpha denotes the angular acceleration, alpha is equal to Fr over I, or Fr over 1/2 mr squared, right? And we can simplify that to get 2F over mr. All right, now let's resort to using a kinematic equation. Delta omega equals alpha delta t. So delta omega equals 2F delta t over mr. Okay, so let's now isolate F. F is equal to mr delta omega all over 2 delta t. So m is 50, r is 2, delta omega is, let's see, pi minus 0, all over 2 times 60. Okay, you can see that the 2's cancel, and you can divide the top and bottom by 10, and we will get that the necessary force is 5.6 pi newtons. All right, now let's calculate the kinetic energy. The kinetic energy is 1/2 I omega squared, and we're going to use the final value because we want to know the kinetic energy after 1 minute. So we're going to use the final angular velocity. So 1/2 times 1/2 mr squared omega final squared, or 1/4 times 50 times 2 squared times pi squared. So the 2 squared and the 1/4 cancel, so we get 50 pi squared joules. All right. Now, I'd like you to try to solve one. All right. Someone taps a 2 kilogram hollow ball, in other words, like a basketball or a soccer ball, with a diameter of 0.3 meters, setting it spinning in place. What is the angular acceleration, assuming an average applied force of 3 newtons? Also, what is the kinetic energy after 1 minute? So if you've ever seen somebody balance a basketball on one finger and then they tap it to keep it moving, keep it rotating in place, okay? Or you can imagine somebody placing a soccer ball on the ground and tapping it so that it spins in place. So for such a system with the given parameters, try to calculate the angular acceleration and also the kinetic energy after 1 minute. So pause the video and try to do that now, please, if you wish. All right, I'll go ahead and work it out myself also. So let me first list the given information. So the mass is 2 kilograms, and I'll denote that by m. The radius is half the diameter, so 0.3 divided by 2 meters. The applied force, I'll denote that by F, the average applied force. That's 3 newtons. And we know that the initial angular velocity was 0 radians per second. All right. Now, let's use what we know about such systems. So, we know that the ball is a hollow sphere, so the moment of inertia is 2/3 mr squared. And we know that the torque due to the applied force is equal to Fr, which is also equal to I alpha. So apparently alpha is equal to Fr over I, or Fr over 2/3 mr squared. And that simplifies to, let's see, 3F over 2mr. All right, so then we can plug in numbers. 3 times 3 divided by 2 times 2 times 0.3 divided by 2. And so, let's see, we get some cancellation. 3 divided by 0.3, that's 10. And 30 divided by 2, that gives us 15 radians per second squared. I hope that's what you got. Okay? Now, we can calculate the kinetic energy using the formula for that. So the formula for kinetic energy is 1/2 I omega squared. So 1/2 times 2/3 mr squared times, and by the way, we're using the final angular velocity because we want to know after 1 minute. So I'm going to use omega sub final, and we're talking about the final 1 minute later, so delta t is equal to 60 seconds if we denote it in minutes. So let's see if we can calculate omega final. We'll use the kinetic energy, we'll use the kinematics formula that delta omega is equal to alpha delta t. So omega final minus omega naught equals alpha delta t. So omega final is equal to omega naught plus alpha delta t. So now let's plug in numbers to our kinetic energy formula after a little bit of simplification. So we get 1/3 times m, which is 2, times r squared, which is 0.3 over 2 squared, and then omega final squared, that's 0, plus 15 times 60 squared. Putting that into our calculator, we get that the kinetic energy is 12,000 joules.